Hello, guys.
Hello.
Okay, so we're gonna start today in another timer. Okay, it's a sophisticated one, not like System. It's a much broad timer in our microcontroller. It's called the timer A. Okay, and actually it's not one timer; they are four. Okay, so this timer, as I said, has four timers, so submodules. Okay. Uh, timer 0, timer A is 0, timer A1, timer A2, timer A3. All of them are called timer A. Okay, although they are just independent timers. Okay. Maybe they call it they call them timer A, then submodules timer A0, A1, 2, 3, because they are very similar in their you can configure them in the same way. So they are basically the same timer, but we can say four independent instances. Okay. Each one of these timers has what's called roll of value or roll over value. This let's roll over value, or the overflow value. So each one of those has its roll over value is 4f, as we will see later. Okay. And we can configure these timers to generate interrupts as well. So timer A has any one of these timers, or timer A in general has four different modes of operation. Okay, for the stop mode means you will stop. Okay, up mode means count up. You are counting up until some value, then you start again. Okay, and you have what's called the continuous mode, which is exactly the up mode, but in that mode you will count until the maximum value. So the maximum value or the roll over value is 4f, f, or around 65,000 count. So if it's fixed 65,000 count, how we can change the time? Then you can configure or change the clock. So the time of one count will change. Okay. So for example, if the clock is 3 megahertz, okay, then one count will be 1 over 3 megahertz, okay, around 0.33 microseconds. If the clock is 6 megahertz, I'm sorry, 1.5 megahertz, just half of this, then the one count will be 0.66 microseconds, doubled. Okay, so for the same count, you may have different time based on the clock that you are using. The fourth mode is called up-down mode, in which you count up, then you count down. Okay, then you count up again and so on. As we see here, we will have some idea about the registers. We will not go into deep in the registers. We will just use driver lib. Okay. So for example, there is a register there, like a configure. You can consider it as a configuration register or something, which has 2 bits called MC bits. And these MC bits, when you configure them as 00, then you are stopping the timer basically. If you configure them as 01, you are configure the timer to work as an up timer or up counter, and so on. Okay. Another register is called register called TAXCCR0. X here is 0, 1, 2, 3 because you have 4 timers. Okay. So in each one of these timers, there is a register called TAXCCR0. Okay. And in this register, you put, the desired rollover value. So the maximum rollover value is 4F. You can't exceed this. If it's in continuous mode, it will count to this value, then reset. Go back to 0 again. Rollover, okay? But using this guy here, if you are in up mode or up down mode, you must put some value here less than or equal to 4F, so that you can change the rollover value of your counter. Okay. Timer A also can generate interrupts, and there are many, basically two types of interrupt. The first one is called the rollover interrupt, okay, which happens with the continuous mode. And this guy is easy, you just count until you reach F, then you start again from 0, and you will have interrupt. If you write some interrupt service routine, you will find that the execution goes to this interrupt service routine. Okay. Also, before we continue, again, here we are, get to know two other registers. Although, again, we will not digging deep in these registers. A register called TAXR. Okay. Basically, this is like the var register of SysTick, if you remember it. This var register, usually you can read the current count of the counter. So whenever you check this register, okay, you will find the current count of that register. And basically you have 4 of them, because you have 4 timers, TA0, TA1, 2, 3. So you have TA0R, TA1R, TA2R, TA3R. Another register, again, there is another register that has some bit called CCIFG, interrupt flag. CC means capture and compare. We will just go into it after 1 minute or something. So CCIFG is the name of the bit which turns to 1 from 0 to 1 whenever you have interrupt. Whenever an interrupt triggers. Okay. So basically, the first type of interrupts is very simple. It's called rollover interrupt. Just like SysTick. SysTick has the same interrupt as well. You put some value in SysTick in the load register. Then whenever the count reaches this value, you will trigger interrupt. It's basically the same. Okay. Another interrupt which has also two setup called capture and compare interrupt. Capture and compare interrupt. Okay. And as you see, there are two uses of that guy. The first use is also simple. It's just like the rollover interrupt, but you are not counting until 4F. You will set up some value in TAXCCRN register. Okay, you will put value there. Then whenever the value, the current count, which is in the TAXR register, reaches that value, then you will have interrupt. The interrupt service routine or the interrupt will trigger, and you, of course, will convert you to the interrupt service routine to execute it. Okay, and you will find this bit, which is CCIFG bit, is 1. Okay. Now, before we go to the next type of interrupt, which is called the capture interrupt, let's also know this register. So when you hear that there is a register called TXCRCR0, okay? Actually, this guy 0, you have also TAXCCR1, 2, 3, 4. They are 5. So each submodule has 5 registers, and you can use 5 registers. And you can use any of them, to put this value to trigger the interrupt. Okay. Good. The second interrupt. So this is called the compare interrupt, because you are comparing not against 4F, you are comparing against some value less than 4f. Okay. The second type of interrupt is called the capture interrupt, in which you are waiting for a signal. So the counter is or the timer is counting or timing. And if you set up some input, for example, GPIO input, to receive some signal, some output signal, okay? Then whenever this signal reaches, or reaches mean converts from 0 to 1 or 1 to 0, okay? Triggers. Whenever you have this event, the current value or the current timer or count in TX register will be copied to TX CCRN register. Then, for example, you can know at what time this signal, reaches or converted from 0 to 1 or 1 to 0. Or, for example, you can know at which time the robot, for example, hit a wall. So, for example, this signal can be the switch, the bumper switch signal. When the bumper switch is hit, the value of this of the input usually goes from 1 to 0. So, for example, if you set your robot to walk, then at some time it hits a wall, then this value, this input from the bumper switch will change from 1 to 0. Then at that time, you will trigger interrupt. And if you check this register, you will find some count. This count is representing, if you multiply it by the counter, by the clock time, you will get the exact time at which the robot hits the wall. So this is an example just to understand it. This is an example here. You have a robot, it should have a bumper switch, although this picture has no bumper switch. So whenever this guy hits the wall, okay, the current count in TX register will be copied to TX CCRN register. Any one of the registers, you will define it 0, 1, 2, 3, 4, 5, or 4. I'm sorry, just until 4. Okay, then you can, if you multiply this value by t clock, the time of a clock. For example, if the clock is 3 megahertz, then you multiply this value by 1 over 3 megahertz. Then you get the time of the trip from that position until it hits the wall. Okay. Okay. Another application also. So this is the capture. This is an example for the capture interrupt. Let's see now examples for the compare interrupts, because it's more interesting. So the compare interrupts actually has modes. Okay, there are also some sub modes inside or subtypes, for example, of this compare interrupt. So, for example, the first one is called set. So whenever you reach some count, some predefined count, you set a signal from 0 to 1. Okay, so you can define some bin on the microcontroller, and this bin will turn to 1 whenever this count reaches some value. Another mode is called toggle reset. Okay, I will not go into detail of this because I will give examples, very good examples after just 3 minutes. Okay, but we just highlight them all. Toggle reset. So you, under some condition, you toggle an output, okay, from 0 to 1 or 1 to 0, whatever its value, you just flip it. And under another condition, you reset it, you make it 0. Set reset. Under some condition, you set. Another condition, you reset. Toggle, you are just toggling. So you can, this is just like the first one, like the set mode, in which you have some output. This output will be 1 or 0. Whenever the timer reaches some count or some time, it will toggle the value from 1 to 0 or 0 to 1. Reset, it's the opposite of set. So again, when the timer reaches some value, reset the output. You make it 0, whatever its previous value. And toggle set, under some condition, you toggle the output from 0 to 1 or 1 to 0. And another condition, you set the value, make it, or the output makes it 1. Finally, resets it. Under some condition, you reset the output, make it 0 all the time. And under another condition, you make it 1. Let's go, because it's not clear. Let's go and have some examples. Okay? You know that your timer can work either up, roll over, or and up count. Up down count. In the up mode, let's see all the 7 modes that I showed you. Set, reset, toggle, set, reset, toggle reset, and toggle set, every one of these. Okay, here all the examples here. So the basic mode, the main configuration is up mode. Now for this example, up mode. Then you choose the set interrupt, which means whenever the timer value reaches some value that you write it to some register called the TAXCCRN. And as example here, 1, you use number 1 of them. Okay. Then you set the output, you make it 1. If it was 0, it will become 1. If it was 1, of course, it will continue 1. Okay. Still, we are in the up mode, but now toggle reset. So under some condition, you toggle. Under another condition, you reset. So the first condition, which is the toggling, is tied to the value in this register, TAXCCRN. And as example here, 1. So whenever the count reaches that value, you will reset, you will toggle, I'm sorry. So if the previous output was 0, you will make it 1. If it was 1, you will make it 0. This is just an example here. Then, whenever the value of the count reaches TXCCR0 now, okay, you reset. So this is the second condition. So you have first condition, or first action, we can say, which is the toggling, is tied to the value inside the TXCCRN, and the N is 1, 2, 3, 4. And the second condition is tied to TXCCR0. Okay, so you have 2 values. One in TXCCR0, and another one will be in any one of the other registers. 1, 2, 3, 4. So you have another 4 registers. Okay. One action is tied to TXCCRN, and then is 1, 2, 3, 4. The other condition or action is tied to the value in TXCCR0. Okay. And if you just look nicely here, this is like PWM signal, right? So the main application for all such headache, okay, is to generate PWM signal. Okay, or yeah, the main application. And it will be something like this. Set reset. First condition is tied to TXCCR1. This is an example, maybe 2 or 3 or 4. So you will set when the timer value reaches this value. You are setting here. If of course, if the previous output was 1, then it will continue 1. Then you reset when the timer reached the value in CCR0 register. Okay, toggle. You will toggle now based on one value, which is TXCCRN. N can be 1, 2, 3, 4. So here the timer reaches this value. So you are toggling from 0 to 1. You continue. Still the timer didn't, cross this value again. I'm crossing it in up mode. This cross is from high to low. It's not counted. But then when it reaches 0, then count again. At that point, the value of the counter exceeds TXCCR up mode. Okay, let's continue. Okay, then toggle set. We stop that here. Toggle set. So in toggle set, we will toggle based on the value in txccr1. Okay, so here, for example, it was some bin, we will see that in a moment. Some output bin when the microcontroller has one previously, then it will convert from 1 to 0 because we will toggle here. Then when we reach CCR 0, it will set from 0 to 1. Then toggle here from 1 to 0, then set. Finally, reset set. You reset upon reaching CCR1 and resetting upon reaching CCR0. So if we assume the previous value was 1, then it will reset here. Then it will set here because the value reaches CCR0. You guys understand that, or it's confusing? Any questions? This is clear? And you feel happy? Oh,
Yeah, it makes clear to me, Professor. Maybe just some example would help clear
okay.
it up a little bit more.
Okay. Now in continuous mode, okay, just I will explain the two other modes, then we have an example, okay. So in the continuous mode, again we will set two registers, TXCCR1 and TXCCR0. Not one again. One is just an example. So what's basically constant here or fixed is the use of TXCCR0, which is tied to the second action, if there is a second action. Okay. The first action is usually tied to TXCCRN because again we have TXCCR1, 2, 3, 4, and 0. But 0 has special use, okay, to confirm the second or to implement the second action. Okay, let's also have this example. Here in the continuous mode, we are counting until we reach the maximum value possible, which is 4f. Okay, so set. Again, this is one condition. So we are tied to register TXCCRN, in this case 1. So whenever you reach the count, you set. There is no action here because we are setting, but the output itself was 1, so we just continue 1. Toggle reset. So we toggle upon reaching CCR1 from 0 to 1, for example. If the start was 1, we will go to 0, the opposite. Then here we reached CCR0, then we reset. Here we will toggle from 0 to 1, then reset. Then set reset, set with CCR1, reset with CCR0, so on. Toggle, there is no second action, so it's only one action, so we will care about only CCR1. So whenever we exceed here, we toggle from 0 to 1, then we exceed again here, so we toggle again from 1 to 0. Reset, still the same, one action, so we only look at CCR1. We reset it here, then at that time here, we will not do anything because it's already 0. It's already resetted. Toggle set, toggle with this guy from 1 to 0. If the start was 0, then we'll go up. Okay. Then here we will set. So we just put 1, whatever the previous value is. And finally, set, we reset with CCR1 and we set with CCR0. Okay. The only difference between that guy and that guy is that here the rollover is also CCR0, but here the rollover is is fixed at 4F. Okay, and this will it changes the signals a little bit. If you compare both, you will have slight change. Okay. Finally, down, let's see. Sorry again. Okay, so we reached that point here. Okay, so in the up-down mode, the first action can happen in both up when we go up or when we go down. Okay, that's the basic difference. The second action always happens with TXCCR0, which has a rollover value. Okay, so it's not up or down. Okay, so for example, here let's take one example, and you guys do the rest. Let's take, for example, reset and set. Okay, so we reset with CCR2 in that example, and we set with CCR0. So here we reached CCR2 in the up mode. We should reset. The output was 0, so it will not change. We reset it, make it again 0. Then we set with TTXCCR0, so from 0 to 1. Then here again, we reached CCR0, but in the down mode. Then we reset again. So this was 1, it will be 0. And it will continue 0 until that point in which, I'm sorry, here we also reset, so no change because it was 0 originally. At that point we set, then here we reset, and so on. It should be easy, okay? Before we go to an example, last thing that I want to cover here is the clocking inside for our microcontroller. So there are two sources for clocks. The first one came from external crystals. You guys has any information about, any idea about this crystal oscillators? So there is something called the crystal oscillators that can generate clocks for us. This clock signals square wave. Okay, and in our microcontroller there are two here. Okay, you can just look at them. Yeah. So there are two. One to generate low frequency crystal, 32 kilohertz. And the other one is high frequency crystal, which generates 48 megahertz. This is kilo, this is mega. Okay. And those guys are located outside. Here is a microcontroller, it's outside the microcontroller. Okay. Another clock source called DCO, or digital controlled oscillator, and this guy is internal inside the microcontroller itself. Okay, and it can be configured to generate any clocks from 1.5 mega until 48 megahertz. Okay, these are the clock sources. Now the clock signals. Okay, there are 3 different clock signals. So we have a clock source, is the module that generates the clock. Then the clock signal, we also in this microcontroller we classify them into three main types. The first one is called auxiliary clock, and this usually has a very low frequency. Okay.
Professor.
Yes.
One of my friends got disconnected when you disconnected, and he's waiting to be let back in the class.
Oh.
I'm not sure if it's showing up for you.
No, it doesn't. Let me check. In the beginning, I was 12, and we're still 12. I don't know.
Oh, it says 11 for me.
So I have a problem here. Let me check.
I thought we were at like 13 or 14 earlier.
Yeah, I think He said he got disconnected and he's just waiting to be let back in.
Can he press the button? I mean, click on the Alan. Okay, I found it now. Okay. I think now he should be in.
Yeah, I see him now. He's in.
Okay. Okay. So we have three different clocks. Okay. One is called auxiliary clock, and this is usually very small in kilohertz. That's why it's connected here to the low frequency oscillator, which maximum can generate 32 kilohertz. And internally inside the micro, you can there is what's called clock dividers. This clock divider can even, so this is the original clock here. So the output here is the original clock, 32 kilohertz. These dividers can even divide more on some integers so that you can generate even smaller clocks. So, for example, if you divide by 1, of course, you will get the same clock. If you divide by 2, you will get 16 kilohertz clock, and so on. Okay. So if you're, for example, if you're gonna, light up a LED, blink a LED, 0 and 1 with a rate of 1 second, which is very, very low. Okay. So at that time, if you want to use a timer to do that, tie this timer to the auxiliary clock, because it usually have very low frequency, so you can save some power, because high frequency means high power. Another clock, it's called master clock. Okay, and the master clock usually masters, or clock the execution of the program itself. Okay. Submaster clock, it's usually, as the name suggests, it's submaster clock. So it may be same as to the master clock, or even smaller than the master clock. Okay, but both are usually in megahertz. The auxiliary usually in very slow, in kilohertz or something. Okay. Okay, luckily we can, configure our clocks all from software using some commands. So previously we were going to that file and it changes this 3 megahertz to 1.5 or 48. I will show you now how to do that, in program. Okay, this is the first example. So this example is basically from Texas Instruments. They have many solved examples there. So you guys can go there and check if you're stuck someday. So this example here generates or blink LED 1, okay, which is started to pin 1.0, and it uses the auxiliary clock, and yeah, it uses with 32 kilohertz. Okay, what else? Yeah, that's it. Okay, and it uses a timer in its continuous overflow mode, in which it reaches 4F, then go down. So when it reaches 4F, for example, it will generate 1, then you toggle. Okay, so whenever you have this rollover, you will toggle the output to the LED. So let's see and examine line by line. First, to configure the timer, any timer, okay, you use a structure. You guys, if you watch my lecture on Introduction to C Programming, I covered this concept, what's called structure. Okay, so a structure is like an array which holds, different type of variables. It may have, for example, integer value, variables in floating, or double variables in character. All this mix can be in one place. The array can have only one type of variables, either float or integer, whatever. So in that structure, you put your configuration, what configuration you need for the timer. Okay. So for example, the clock source. Okay. So you, as a program suggested, it wanna use auxiliary clock. So here is, if you write this line here, of course this comes from the driver library PDF. You guys go there, you will find this. If you wanna use the auxiliary clock, you put this line here. Then comma, you put the clock divider. Do you want the auxiliary clock as it is, or you want, for example, half of it, or 1/4 of it? So here it wanna blink the LED based on the exact auxiliary clock. So the divider here is 1. So we here with this line here, we also define the clock division. Okay, if you change 1 to 2, since the clock input is 32, but what you're gonna see is 32/2, which is 16 kilohertz. You wanna generate interrupt when it's roll over, so you go there and toggle the LED. So here you enable the interrupt. Okay. And this line here with this structure, or this, value, if you write this exact line, you are enabling the overflow interrupt, or the rollover interrupt. So you will work basically in the continuous mode. And in the setup, usually we prefer to to clear the current time, or the current counter, which is in TAXR register, if you remember. Okay, so this line here will clear the register. Okay, then the main function. First, you define B10 as a GPIO output to link the LED. Okay, and you put initially 0 there, so initially the LED will be off. What else? Here you start this clock, okay, or you define the reference clock that you're gonna use. And here, yes. So if you define the reference clock with, for example, whatever the value is, for example, 128 kilohertz, but you want 32 kilohertz, then you must divide. So guys, I will turn off my video. Okay, so I'm sorry for this. I don't know why we have such difficulties this day. Anyways. Okay, so I don't want you guys to worry about these two lines of code, okay, in which you define the clock signal or something. So this will be given for you, okay? So if I give you a homework or something, I will tell you what exactly to write here, okay? What else we have? Yeah. Then this is a line of code that will actually, configure, will send this configuration to the hardware of the timer. Okay. So map timer A, configure continuous mode. Okay. Then here you put the name of the structure. I'm sorry, the name of the timer that you want to use. If you want to use timer is timer 0, you put 0 here. If you want timer 1, you put 1, 2, 3. So you have 4 timers from 0 to 3. What you only want to change is that A0 will become A1 or A2 or A3. Then you put here the name and the address of the structure, which have the configuration of the timer. Okay. So this structure here has this name. So you put the name, and the ampersand here means, go to this address and get the information from there. This is how you configure the interrupt. This is not my way, okay? So this is the TI way of configuring their interrupt. I'm sorry, their timers. Is you put your configuration in in a structure. And by the way, this structure has special naming. You must name it. You must give it this name. For example, if it's in continuous mode, if it's an up mode, it should have another name. If it's up down, it should have another name. If it will generate a PWM signal, as you will see later, it will have a different name. But you can change this guy. So this name here you can change. So this is like integer, float, double. This is just a keyword, but you can configure. You can change this. Okay. Here also, you remember, guys, the stuff for the interrupt disable and enable. I commented this line here, okay, but it's just like watch for it is just similar to watch for interrupt. Okay, if you comment this line, it will not hurt you. Okay, but basically it puts the microcontroller into sleep until it configures the interrupt. Then you go to the while loop and do the same stuff again. Here you enable the interrupt, okay, and for interrupt 0 you should write this keyword here, int ta0n. This is a keyword from TI. You cannot use another name. Then you enable all the interrupts on your microcontroller, and finally here you are starting this is like an order or something, a command to the hardware to start the timer itself. So map timer A start counter. Then you put here the timer that you meant. Maybe you have many, you configure or define many timers, okay, and in what mode you wanna start it, okay. The interrupt service routine is simple, okay. Whenever you go there, and you will go there when you reaches F. So basically, you will toggle the output on pin 1.0. So the LED will blink. And also an important step here is that you must clear the interrupt flag, this CCIFG, this pin here. I said that there is a pin called I'm sorry, not a bit, called CCIFG that will go to 1 whenever you have an interrupt. So you must clear this pin whenever you go to the interrupt service. If you didn't clear it, it will kick all the time. Okay, it will not look at the timer, it will just kick all the time.
Because I was gonna add another main.c file in the same like folder that I have for today's lab.
Why?
Well, I was just asking if you can do that because I don't want to like create another folder.
I didn't get that. So what I should do for you? What do you want me to do?
Can I share my screen?
Yeah, of course.
Oh, you can't. Oh, okay.
Professor, I'm done with mine.
Okay, Mr. Gustavo, thank you.
Professor, can you show the first part of the code again so I can snip it real quick?
Of course. So did you share, Johnny, or? Did you share, Johnny?
I think Clark answered my question in the chat.
I look. Some people do that. They put both mains at the same time, but they name, for example, one of them like main old or something. So it will be like just like a function. So you can switch between them by renaming them. You understand?
Basically,
exists.
can't call it main.c. You have to call it main
Oh,
old.c.
yeah. Yes, yes. So if you are very lazy and you don't want to make another project, okay, you can do something like this. Let me write this down here. Because it's a different keyboard.
Yeah, I think that I've been creating a lot of folders. And
Main, I understand. You can do something like this. Look.
well, I can't see your computer screen.
Inbox here some junk. Okay. Ever. Okay, my friend. Then, if you wanna work with this one, make it main and call this main underscore whatever, you know, or main one and main two, something like this. Then, if you wanna work with the other one, I'm sorry, with this, name this, you know, main one. You know, you got the idea. You can do that. Okay.
Professor,
Yes, Clark.
could you go back to the B17 timer A PWM that you were showing earlier, the start of it? I wasn't able to get the functions at the beginning. Thank you.
Jose, do you have a problem, Jose?
I had a bit of trouble, but I'm figuring it out right now. I just found my error with the code.
Okay, Ivan. Thank you very much, Ivan. I see the ultrasound sensors.
Oh yeah, it makes it so top heavy though. I need to like add something on the back.
Yeah. Okay, let's continue now with the other part. So I will get my screen here. Okay, so the other application we're going to take today is BWM stuff. Okay. So let me share my screen. Yeah. So you can configure timer A to generate BWM signals. Okay. Actually, you can use the up down, you know, or the up, or you know, the rollover, all such, you know, stuff to do that for you. But you can do that directly using a BWM structure. Okay. So again, based on the presentations that we just, you know, my slides, let's look at them very quick. You can configure it, for example, in up mode or continuous mode, like this example here. Then by configuring a proper values for CCR1 and CCR0, you can generate BWM signal. So for example, this is a BWM signal with how much exactly? We measure, yeah, with 33%, I'm sorry, 67% duty cycle. Okay. Here it is 33% duty cycle. Okay, so you can use, you know, the continuous mode to generate with some, and you set up proper values for TXCCR0 and TXCCR1 or 2 or 3 or 4 to generate a PWM signal. But also you can do that, so there is also the ability, a built-in ability to generate a PWM signal using a PWM structure. Okay, so that structure has some entries, just like the previous example. The previous example, the structure has 4 entries. Okay, here we have also special type of entries. So before I go over that, I will show you guys from where we get this information. Of course, there should be some document that tells us that if you want to generate a PWM signal, you write a structure like this, and you populate this structure with these entries. Okay, this is actually come from the this guy, the driver lib. So let's write PWM here. I don't know if this is or not. Yeah. Okay. But better, you can go better to the, yes. So here all the structures that you can build for timer A. Okay. And this is the structures that work. Oops. That goes so far. Let's go back. So timer A, timer A. Timer PWM config. I'm gonna search it because the link is not good. Oh, this is actually yes. Oh, still. Yeah, here is a structure. Okay, and here is the entries or the populations that you can, or the parameters that you're gonna put inside this structure. So this structure has 1, 2, 3, 4, 5, 6 entries. So let's go one by one of them. So first, it's a clock source. Which clock you wanna use? Okay, is this the auxiliary clock, submaster clock, some external clock, for example, I don't know what is this exactly. It's also this is inverter. I don't know. Some external and both are external sources. But basically we're gonna concentrate on this auxiliary clock and submaster clock. Okay, you wanna use the auxiliary clock or the submaster clock as it is, or you wanna decrease or reduce the frequency. So here you define the second parameter, which is the clock divider. So you put timer A, clock source, divider 1, then you will take this or this or this or this, any one of those as it is. If you write timer A, clock source, divider 2, then you're gonna divide by 2, and so on. Okay. The third entry is the timer period. Okay, this is a value that should be less than or equal to f. Okay. And this value will actually be stored in TAXCCR0 register. If you go back to this guy here, this register, TAXCCR0. Okay. Then, then how about what kind of register you're gonna use? So for example, if we go back here, we were using TXCCR1 in that example. In that example also in that example we're using TXCCR2. You can use whatever register you want. You have 5 registers, 0, 1, 2, 3, 4. So 0 is reserved. You can use 1 or 2 or 3 or 4. Okay. So in that entry here, register, compare register, you can use 1, 2, 3. Of course, you can't use 0. But here, this user's guide is for many microcontrollers, not only ours. Okay. So in our case, you can use until 4. Okay, guys. Then here you define what kind of set reset these modes that we show here. So for example here there are many modes: set mode, toggle reset, set reset, toggle reset. All these modes are defined in that field, in the fifth field, which is the compare output mode. Okay. Finally, you here define the duty cycle, but you are not putting here 20%, 25. No, you put a number, and the ratio between this number and this number, the time period, will give you the duty cycle. So let's go back to the examples that I'm giving here. So here we are defining a PWM configuration for the timer A. We define the clock source to be submaster clock. Okay, you divide this clock source by 64. Then here you define the maximum count, which maximum for F. Here you define it in decimal as 40,000. Of course, so 40,000 is less than F. We will use register TAX CCR3. Okay, and we're gonna use reset set, this mode here. You can recall reset set, this one. And what else? Yeah, here's the duty cycle. Here I am putting 10,000. If you divide 10,000 by 40,000, this is 25% duty cycle. And this number will actually go to this register. I'm sorry. This, where is this guy? This register in that example here, TXCCR2 or TXCCR3. In our example, TXCCR3. Okay. So this is the configuration of the timer. Now the main. Okay. I will not, as you see, guys, there is cystic here. I will not touch this cystic now. I will explain it at the end. So first we define here the frequency, 3 million. Okay. Here you are defining the input clock from a digital controlled oscillator. Okay. Then here you define the relation between your clock that you're gonna use, which is a submaster clock, and the main clock. Okay. So we have we will use submaster clock. We will connect it to the DCO clock, and the divider is 1. Okay. So we just take it as it is, but the timer itself will take the submaster clock and divide it by 64. Remember, here you can make 2 divisions. You can divide here and you can divide here. So if, for example, now with this configuration, the input clock to timer A is how much? 3 million. This number, whatever it is, let's copy and paste. Divided by 64. How about if we did this? I will put it in a comment so you guys don't give you. If we put here 16 or 4. So the input clock is 3 million. Okay. Then we divide it first by 4. This will give you the submaster clock. Then the timer will receive this clock divided by 64. The timer will receive a clock equal to submaster clock over 64 which is equal to this guy divided by 64. Okay? So you can play around with the dividers to get to the clock you want or you desire. Okay? Again, I will not touch Systic now. Let's continue. Good. Now you want to generate BWM signal. Okay? So this signal should go out of the, should drive, for example, the motor, or it should drive, for example, LED 1. So you must define a bit or a bin on your microcontroller from which you will receive this signal, this BWM signal. Okay, and for that we should go back to the presentation here. 6.6. Okay. So in the presentation, in the far beginning here, look, here are the pins that are connected, the microcontrollers that are connected to our timers, the 4 timers. Okay, so for example, timer 0, timer A0, you can use any of these 5 pins on your microcontroller to generate, for example, a BWM out of this guy, the timer 0. Okay. Again, similar to timer 1, but different pins. Timer 3, again, different set of pins, and timer 2, different set of pins. Okay. Now let's look at B6.6. B6, where is it? Yes, this one. This is the one that we are using right now. So this pin here is part of timer 2. Okay, so we will use timer 2. Okay. And yeah, it's timer 2. And yeah, and it's also bounded to TE2.3 means TE2 here is 2 is TX CCR2. Okay, so it will be register 2. Okay, so if we connect, let's copy and paste that. I'm sorry, no, it will not be covered. So let's hope it somehow. Yes, no, it doesn't. Oh, this trick sometimes doesn't work. Anyways, let's put this side by side and relate stuff together. Okay. So we are using here, as you see, guys, here we are using capture compare register 3. Okay, TX-CCR3. So why is that? Because we want to use bin 6.6, and bin 6.6 is tied to register 3. Timer 2, register 3. Okay, timer 2, register 3. So bin 6.6 default operation is a GPIO bin. If you want to use it as a part of a timer, you should change its functionality from a GPIO to its another. You remember, guys, any bin has at most 4 different functionality. GPIO, in which you configure the selection bits as 00. Then you have a primary, secondary, and tertiary. If you remember, guys, this is maybe 1 month ago or something. Okay, so the timer functionality for this bin is a primary functionality. So with this line of code here, you are defining or you are configuring this bin 6.6 as a primary with its primary functionality, which is a timer. Okay, output for the timer. Okay, so with this, we're gonna output our BWM signal from B6.6. Then you send the configuration to the timer. So you put here the address of the structure, okay, and you define the timer that you're gonna use. So B6.6 is part of timer 2. That's why we put timer 2 here. Timer 2. Okay. Then you disable master, then you enable. This is for SysTech. We will not touch it now. Just let me recap first all the numbers because we have many numbers. So the type of timer is timer 2. So that's why we use timer 2 here. Okay. We are using in timer 2, we are using register 3, TTAX, TA2, CCR3. Okay. That's why we have here capture compare register 3. And this register can, generate output to bin B6.6. So that's why we configured here B6.6 as with its primary functionality, which is output for the timer TE2. Okay. So it's a little bit confusing, but we have mainly 3 numbers. The timer submodule number. So the timer submodule number is 2. We have the capture compare register that we are using in that timer. Timer A2 bin 6.6 is connected to register 3. That's why we configure this register here, or you use this register here. We're gonna use bin 6.6 as an output for us. So we configure it with its primary functionality. You should know this information because in the assignment, which will be published by Wednesday, not today. Okay, we'll ask you to use some other bins here, not B6.6. So you should be able to configure any bin or any timer using the same procedure. Okay. Good. So now what is the relation of SysTech here? So basically SysTech here, I'm using SysTech, which is another timer, by the way, of course, is to change the BWM duty cycle. So in the beginning, the primary, our default duty cycle based on our configuration here is 25% because this is 10,000 and this is 40,000. Okay. The good thing is that we can change at runtime the duty cycle by changing the value in that register. Let's go back here. Yeah. If you change the value in that register, okay, which in our case, TAX, TA2, CCR3, then you can change the duty cycle. Okay. So I configured SysTech to make interrupt each 10 seconds. And in the interrupt service routine, I am writing to this register, timer A, capture compare register 3, this one. This is a keyword in reserved for that register. So this register, when you want to configure its value, you can write this name here, which refer to timer A2 CCR3 register, and you put here the desired value. So each time I call this interrupt service routine, I will increase the duration by 10,000. So in the beginning, the duty cycle is 25%. When I add 10,000, it will be TE2 CCRC will be 20,000, which is 50%, then 75%, then 100%. Then it will go back to 25%. So let's run this code and see what's gonna happen with it. There is no LED here. Okay, we'll just look at the oscilloscope. So let's put breakpoint. So I want to show you guys what I'm doing here. So we are using bin 6.6. Okay. So you guys can see. Look at my kit here. So you see, guys, you get this line, this column here of bins. One of them is B6.6. So I will put my oscilloscope at that point, B6.6. I'm not sure if you can see. Okay, so that column here, near or close to the left motor, one of the pins, if you check the what's written beside, it's called pin 6.6. Okay, so look now at the output. It's 25%. Okay. If you look at my screen, now Systic has go to the interrupt service routine. Oh yeah, because it's working all the time. Yeah. So each 10 seconds, Systic interrupt service routine, kicks in and they change the duty cycle. I have just one problem in that code here because there is no problems here. So this is now 100% duty cycle, then 25%, then 50%, 27%, 75%, I'm sorry, then 100%. Okay? So this code is very important for you because I'm gonna ask you about other bins to do the same stuff but on other bins, but not today. Okay? Okay, guys, did you finish this?
Yeah.
Yeah.
You
Yeah.
want to share a screen, Professor?
No, just because there is no.
Yeah, it doesn't do anything.
Yeah, it doesn't do anything.
What we can do is
You can go by the honor system and just say if we did it or not.
I trust you, but let's make it a little more fun. So you guys can put their lid, okay? So you can toggle a lid. Oh, let's go with the honor system. Okay, let me create a new homework. Okay, what we call it, Systic timer A, adaptive BWM. Systic lecture coding, okay, and available from now until 1 week, and we'll use 1 week as well. So let's go one by one. Alan, you finish?
Yeah, I did.
Okay. So Alan, number 1 customer. Johnny?
Not yet.
Okay. Christopher Bernardo?
Yeah, I'm done.
Okay. Saul?
Yeah.
Good. Hussein?
Not yet.
The first one, did you finish the first one?
The first one, yes. I'll show you in a bit.
Okay. Christian Gonzalez, I think it's not here. Clark?
Yeah, I finished.
Omar is not here. Evan? Even.
Sorry, I had my thing muted. Yeah, I'm done.
Okay. Genesis.
Yeah, I finished, Professor.
Mark is here, or no, I think he's not here. Gustavo.
Done.
Good. Dominic.
Yep, I got it.
Christopher. Will.
Yeah, I finished it.
Okay. So let's have an assignment very quick now. Okay, do the same using switch 1. Okay. So I will stop sharing my screen. Okay. I think I stopped it already. Yeah. I have here another code that do the same. I mean, it changes the duty cycle, but based on switch 1. Okay. So whenever you press switch 1, you change the duty cycle. So let me show you on my setup here. Okay. I will run the other code. This should be your homework. You can do it now because we have time still in the lab, or you can do it at home, whatever, after the lab. So let's go here and let's build that guy. It's already built. So let's. Okay. Good. So you guys see here that 25%. Okay. It's very clear, and now let me press the button. Let's look now at the screen. It's 50%. If I press again, go back here, 75%. If I press, 100%. DC. If I press again, it will go back to 25%. Okay?
Professor, so how are we gonna prove this to you? Are we just gonna send you the code?
Oh yeah, you are right, my friend. I don't know.
Can we like tie it to a motor or something?
Yeah, how can we check it?
Yes. Let me think about that. Let me think.
Not really the most interesting.
You can do the following. Basically, TX or TE2 CCR3 is a register. Okay. So you can, whenever you finish, you can put a breakpoint in your code, and then we will see the value of the register changes. Okay. It will first become 1,000. Then when you go back, it will be 2,000. So I can see what's happening. Then we can project it. Yes, if you have, oscilloscope, you will have this kind of behavior. So let me check this myself first. I mean, I check the register. Timer A2. And yes. So I will do that experiment myself now.
Professor,
Yes.
I got the
first one? Okay.
yeah.
Okay.
Professor,
Yes.
can I share my screen from last week's code because I had to leave early?
It's not working yet?
No, I have it working.
Okay, just
I
give
just
me, yeah, give me 2 minutes. 2 minutes.
yeah, no worries, no worries. All right, thank you.
Okay, guys, I will show you now, you know, how this code is changing. So here is, yeah. I'm not sure if you can see this. You can see that, right? You can't see. It's really bad. I can. Yes, right. So I will share my screen now and I show you. Okay. So here is, you can see the register, you know, this. You guys can see the screen?
Yeah.
So here is the registers, okay? And I put a breakpoint in the interrupt service routine. Here is timer A2, okay? And here is the registers that I'm talking about. 0, 1, 2, 3, 4, okay? I'm sorry, 0, 1, 2, 3, 4. Okay, TA, X here is 2, CCR, you know, 4, 3, 2, 1, 0. And we are using this guy, okay? So whenever you go, and I hope it's not showing up. Yeah. So now the breakpoint should be stopped in the interrupt service routine. So if we continue, should it change? Okay. So that's the part in which it's changing. If I continued, look, it's changing. Okay. So you do this assignment. You put a breakpoint, okay, and you just show me if you finish before the 3:30, or you know you just send it to me, and I will do this breakpoint myself and check it myself. Okay. But you can check from the register values here using breakpoints. Okay. So let me publish this homework very quick. Should be easy.
Professor,
Yes, Gustav.
could I show you that code from last week?
Yeah, of course. I'm sorry. I just forgot. Sure.
No worries. Where do I put the breakpoints again? I forgot.
You mean the line tracking stuff, right?
Yeah, to show up that
Show me the
information.
screen. You would you shared the screen. Okay. Let me go down a little bit. Go down. Yeah, put at 44.
Where do I pop up that thing?
I don't know. Let me check.
Are you looking for the variable, Gustavo?
Yeah.
Go to window,
Window.
or actually, my bad, view. It's in view.
Okay.
And then go all the way down to variables. Right up.
No, go.
Oh,
The
there it is.
yes. Yeah. So now you are standing on
In the middle.
the floor. No, the floor now is dark. If it's in the middle, just turn on the switch.
Oh, I forgot to turn it on. My bad. There it is.
Yes. Yeah, now it's in the middle, right?
Oops, I don't know why I did that.
Yes. That's weird because, yeah, it's on the right. Just move it a little bit to the center. Nice. Move it again. Or the other way. You have a big tape, right?
Yeah.
Okay. That's why. If you have a big tape, you can, just not for this assignment or this, you can use only the even sensors or the odd sensors. Okay.
Okay.
That's why there is even and odd to save power.
Right.
If you have, a large track that you are following.
Right. Okay. Is that good?
Yeah, that's good. Thank you.
Thank you.
Mr. Mustafa?
Just 1 second. Jose, did you finish the second one? The second.
Almost done, not yet.
Okay. Yes, John.
I just finished the second one. The
Oh.
second code.
Just give me 1 second again, please, because Gustav, we need to be, yeah. Okay.
What did you say to do afterwards, after the second code?
Just show me your debugging stuff. You should hit the switch, and each time, the value in TX in TA2 CCR3 should be incremented by 1000.
Did you show how to do that, or
Share
were
your
we-
screen. Share your screen. Share your screen. If you finish, share your screen. Go down. No, that's wrong. We want this to be interrupted by switch 1, not by SysTick.
I think that was his question, Professor.
So the interrupt, I want the interrupt to be triggered by pressing a switch, pressing switch 1. You guys know switch 1 or not? So these two switches on the left and right of the.
Yeah, it's port 1, switch 1, right?
Yeah, S1. You have two switches. One is called B1.1 or S1. S1 is B1.1, and the S2 is connected to pin 1.4. I want you to use switch 1, which is connected to B1.1. Whenever you hit this switch, you go to interrupt service routine, some interrupt service routine, and you do exactly the same stuff that you were doing with SysTick. But you will add one extra step in the interrupt service routine when you use the switch. One step that we mentioned before when we take the GPIO interrupts.
Hey, Professor, we can use the system tick handler, right? Do we have to still use the port 1 IRQ handler since we're using the switch?
I want you to trigger the interrupt based on the pressing of the switch. Mm-hmm. This is called the GPIO interrupt. This is not SysTick interrupt. Okay.
Okay.
So the interrupt service routine name should be changed. Just to go back to the lecture in which we took the GPIO interrupt. Okay.
Okay.
And you will see there, something very useful.